वेलकम। तो इस वीडियो में हम जानेंगे कि EDTA सॉल्यूशन कैसे बनाया जाता है और उसको स्टैंडर्डाइज कैसे किया जाता है। तो EDTA की फुल फॉर्म होती है इथिलीन डायमीन टेट्राएसिटिक एसिड। तो इफ आई ड्रॉ द स्ट्रक्चर, सो दिस इज इथिलीन diamine, so this is ethylene diamine and tetraacetic acid. If you want to incorporate in this, so ethylene diamine tetraacetic acid. Here we have, say, if you want to write it sodium salt, say here if we replace one hydrogen by sodium, here also if we replace one hydrogen with sodium, this will be sodium salt of EDTA. We can write it as sodium salt of EDTA. And then in EDTA we have two hydrogen also. Short form we can write of EDTA as Na2H2Y. So short form to write the reactions we can write it in this way. So EDTA solution is used to determine the permanent and temporary as well as then the total hardness of the water. And in this video हम जानेंगे कि EDTA solution कैसे बनाते हैं और उसको हम कैसे स्टैंडर्डाइज करते हैं। तो चलिए देखते हैं कि हम EDTA को कैसे बनाते हैं और कैसे स्टैंडर्डाइज करते हैं। So here it's written that EDTA can be standardized against many reagents such as metallic magnesium, calcium carbonate or metallic bismuth. So generally we are standardizing EDTA solution using calcium carbonate solution. As we have seen that when we are determining the hardness of water, we expressed hardness of water as ppm of calcium carbonate, as majority of the hardness is because of the carbonate ion, and also the method do not distinguishes the calcium from the magnesium ion. So that is why we are expressing the hardness of water as ppm of calcium carbonate. So it is always because since we are expressing it as ppm of calcium carbonate, so it is better to standardize the prepare EDTA solution using calcium carbonate only, although we can use metallic magnesium also or metallic bismuth also. But for best result, EDTA solution is standardized against the same cation and using the same method as will be later used during the sample analysis. So this is structure of EDTA. So this is ethylene diamine tetraacetic acid. This is acetic acid. So here this structure is acetic acid, this structure is acetic. So tetraacetic acid, we have 4 tetraacetic acid, and if we want to write the short form, if it's sodium salt, then as I told you, we can write it as this way, and we can short form also we can write this. For reactions we will use this short form. This is the short form to write EDTA. Okay, so what all apparatus and glassware we require conical flask, volumetric flask, burette, pipette, polyethylene reagent bottle. Okay, so this is how to prepare 0.02 normal EDTA solution. So we will first prepare approximately 0.02 normal near to 0.02 normal, and then we will standardize it using the 0.02 normal calcium carbonate solution. Now EDTA molecular weight is 372.25 gram, and if you want to prepare 0.01 normal of it, you will have to take 3.72 gram, and if you want to prepare 0.02 normal, we will have to take 7.45 around. So we will take slightly higher, we can take 7.48 gram also, because as we know that it is easy to dilute rather than to concentrate. So 7.42 gram, 8 gram can be taken, and volume could be can be made to 1 liter water. With water, if you make up the volume to 1 liter in a volumetric flask, then we will have around 0.02 normal. We don't know how much is the normality because this is not a primary standard. It is not available in pure and crystalline state, so this is not a primary standard, and we'll have to standardize it. So dissolve 7.45 gram of disodium ethylene diamine dihydrogen tetraacetate in distilled water. Make up the volume to 1 liter. Mix well and store in a polyethylene reagent bottle. It is standardized against 0.02 normal calcium carbonate or calcium chloride solution. So here one point to note is that why we make use of polyethylene reagent bottle, and now why we are not storing it in glass bottle, because glass is also having ions, so like sodium, magnesium, prevent it. Here your sodium ion, calcium ion, magnesium ion, aluminum ions all are there in the glass, so these can leach if you store EDTA solution for a long time. So if you're storing it in polyethylene reagent bottle, EDTA will remain stable for a long period of time. That is why we are storing them in polyethylene reagent bottle. Okay, so as I've told you that we have to standardize the prepared 0.02 normal EDTA solution using 0.02 normal calcium carbonate solution. So this is primary standard substance. So this can be, once prepared, we will know that it is 0.02 normal only. So calcium carbonate molecular weight is 100 gram. So if I want to prepare 0.01 normal calcium carbonate solution, then I have to take 1 gram for 1 liter. And if you want to prepare 0.02 normal, obviously we have to take 2 gram for 2 liter. Okay, sorry, for 1 liter to have 0.02 normal calcium carbonate solution. For that 2 gram you have to take for 1 liter. Okay, so how will you prepare standard calcium solution? By weighing 2 gram calcium carbonate into 500 ml conical flask, and then you have to make use of dilute HCl until calcium carbonate dissolves. For dissolving, otherwise calcium carbonate is not dissolved in, as we know, that is not dissolved in water easily. So we have to make use of dilute HCl until calcium carbonate dissolves, and then we will add 20 ml water, boil to expel carbon dioxide. So we have to add 20 ml water, and then we have to boil the solution to expel carbon dioxide and cool. Then we have to add methyl red indicator and adjust the intermediate orange color using ammonium hydroxide or HCl solution. So pH to be maintained in between 6 to 7. This pH is necessary to keep the calcium carbonate solution stable, because if pH is very low, then what will happen, that EDTA won't bind with the calcium ion. And second, if pH is higher, then there is chances that calcium hydroxide precipitate can be formed, or your calcium ion in the solution form won't be there. So it can form calcium carbonate also, it can form calcium hydroxide also if the pH is higher. So that is why we are ensuring using methyl red indicator that the pH is lying between 6 to 7. Transfer to 1 liter volumetric flask and make up to the mark. Store in airtight bottle. Okay, so this is how we are preparing the 0.02 normal calcium carbonate solution. Now, how to standardize it using this? So we are making use of echrome black tea indicator. You have to dissolve 0.5 gram in 100 ml triethanolamine or 0.4 gram in 100 ml methanol. Either way, you can have the echrome black tea indicator. This is blue in color. Now, buffer solution, how to prepare that? We are using ammonical buffer. The reason I will tell you that if we see that there is a release of 4H plus ion during the standardization process. So to maintain the pH in between 9 to 10, which is necessary for the stability of the EDTA and metal ion complex, it is necessary that we make use of ammonical buffer. And dissolve 16.9 gram ammonium chloride in 143 ml ammonium hydroxide, dilute to 250 ml with water, store in tightly stoppered bottle, discard after 1 month or when pH that 10 plus minus 1 fails. Okay, so in this way you are preparing the buffer solution. You have to take 16.9 gram ammonium chloride in 143 ml ammonium hydroxide and dilute it to 250 ml with water. Okay, so how to standardization? Simply you rinse and fill the burette with prepared EDTA solution. You want to know its normality, how much normal is EDTA solution that we want to, so you fill it in the burette. Take 25 ml of standard calcium carbonate solution into 50 ml flask, and then add 1 ml ammonical buffer and 3 to 4 drops of echrome black tea indicator. Then you add 1 ml of ammonical buffer and 3 to 4 drops of echrome black tea indicator. Titrate until color changes from wine red to dark blue. Okay, so 25 ml of standard calcium carbonate is simple, and then you add 1 ml of ammonical buffer. Ammonical buffer, reason I've told you, and 3 to 4 drops of echrome black indicator. You will titrate until your wine red color changes to dark blue. So if you see the structure of echrome black tea, the structure is shown here, and it can be written as NaH2 because there are 2 hydrogen atoms. So here 2 hydrogen atoms are there, so you can write it this, and since it is indicator, I can write it I. So this again can be written as H2IN minus, and at pH 9 to 10 this form is changed to HIN2 minus, and this is the active form of indicator at this pH. So that is why it is necessary to maintain the pH between 9 to 10 to have the indicator in this form, HIN2 minus form. Okay, let us see the reaction. So your calcium carbonate, calcium ion is there in the solution, that will react with the indicator to form metal indicator of that complex. So your calcium indicator complex that will be formed like this, and this will be wine red in color. Okay, the EDTA is there, then we'll start treating with the EDTA. First it will react with the free metal ions which are there in the solution that have not bounded to indicator, and it will form metal EDTA complex. So I can write it here, calcium Y2 minus here, because calcium is the metal ion here. And then here also we can see that 2H plus have been released, 1H plus here has been released, and this the EDTA once all the metal ions which are the calcium ion which are there in the solution have been used by EDTA. It then removes the metal ion from the metal indicator complex that has formed. So it will remove the metal indicator, that is ions metal from the indicator, and from the metal indicator complex as here, and the indicator will release as such, forming the blue color, and that is why at the end you are having blue color in the titration, and there is 1H plus ion released. Total 4H plus ion has been released during the reaction, and that is why it is necessary that to maintain the pH between 9 to 10, which is necessary for indicator to have in this form, and second to have the stability of the metal EDTA complex, it is necessary to maintain the pH. That is why we make use of harmonical buffer. Okay, so these are the reactions which are taking place. And then let's see the procedure. As I already told you, that you simply take 25 ml of standard calcium carbonate solution in 250 ml flask, and then you add 1 ml of harmonical buffer, 3 to 4 drops of echrome black tea indicator, and then titrate when you are from the wine red to the dark blue color. That whatever titer value you are getting, you will put in this formula, and 1 v1 equal to 20 v2. On one side you will have calcium carbonate volume, that how much volume you have taken. So your 25 ml here you have taken, and then how much is the normality, 0.01, 0.02 normality you have taken. So here 25 into normality of the calcium carbonate is 0.02 divided by how much titer value is coming. So from this calculation you will be able to know how much the normality of the EDTA solution you have prepared. Say if it is not, if it is slightly higher, say it is 0.02 normal is there, then how much then you will adjust the normality to 0.02 normal by simple how much if this is to be taken to have 0.02 normal of say 100 ml EDTA solution. So in this formula, using this formula, you will calculate that how much ml of prepared an EDTA solution to be taken and volume made up to 100 ml, so that you have 0.02 normal of EDTA solution. That EDTA solution, once standardized, can be used to determine the hardness, temporary and permanent of water. तो इस तरह से हम EDTA को प्रिपेयर करते हैं, EDTA सॉल्यूशन को प्रिपेयर करते हैं और उसको स्टैंडर्डाइज करते हैं. थैंक यू.